All right, take a breath, take a relaxing breath, because 3.2 is not going to be as intense as 3.1. And in fact, in this video, there's not even that much new stuff. There is quite a few definitions, but not that much new math. Okay, so let's jump right into it. I'm not going to introduce what this section's about just yet. We're going to see what it's about when we start doing some problems. We're going to start with a couple definitions. So first definition, let f be a function. Then the derivative function f prime is given by the equation f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, why do I say this is nothing new? It's because this is the same exact formula we use to calculate the derivative at a point. And that's what this section's all about, is okay, we've calculated the derivative at a point. Now let's calculate the derivative at all the points all at the same time. Okay, so instead of just finding the derivative, the slope of the function once for every point, backwards. Instead of calculating the derivative each time to find the slope at different points, we're calculating the derivative once, and then we can find the slope anywhere we want by just plugging this in. Derivative is slope. Slope of the tangent line is the slope of the function. Slope of the function is the derivative. All these words mean the same thing. Derivative is slope. If we use this formula, which again, we've already done this basically. If we use this equation, we can calculate the slope of a function anywhere we want. We're going to see that in action after a couple more very similar definitions. F is differentiable at a point A. Oops, that's not an A, that's an I. F is differentiable at A if f prime of A exists. Okay, so if the derivative exists, we say it's differentiable at that point. Very similar definitions, right? F is differentiable on a set, on an interval I, if, what is wrong with my, if? That's not how you spell if. IF, not FI. It's differentiable on an interval I if it's differentiable for all A in that interval. Again, this is the element set. Kind of looks like a weird E. That means A in the interval I. So we have differentiability at a point, differentiability on an interval, and finally, f is a differentiable function, period. If, what do you think for this one? Differentiable at a point means the derivative exists at that point. Differentiable on an interval means the derivative exists on that interval. Just saying something's a differentiable function means it's differentiable everywhere on its domain. Okay? So if f prime of A exists on the whole domain of f. Okay? So lots of definitions, but they're basically kind of all the same definition. Differentiability, the derivative function. And that's what we're doing in this video. That's what we're doing in this section. So example 1 shouldn't be too crazy compared to section 3.1. It should be very similar. Find f prime for part A is going to be f of x equals the square root of x. Now we've done this very, very similarly before. We're just going to use this formula and simplify this limit like we did in 3.1. There's just no numbers anymore. but the calculations will be very, very similar. There's the limit as h goes to 0. Copy down that formula, Jason. Again, this is f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. That is what the derivative function is. The derivative function is just equal to this limit, where the limit exists. So the limit as h goes to 0. Be very careful when you're evaluating these. Right, we know f of x equals the square root of x. So we'll replace f of x with the square root of x. So what is f of x plus h? That's still the same function. It's still the square root function. F is the function. F is the square root function. But now it's not an x that's on the inside. It's an x plus h that's going to be on the inside of that square root. So same function, but it's the different input. Okay? So that's how we replace f of x plus h. We get the limit as h goes to 0 of the square root of x plus h minus the square root of x divided by h. And basically with every single derivative, you're not going to be able to use direct substitution at the start. Okay? It's almost always going to be 0 divided by 0. If we try to plug in h equals 0, this limit, 0 over 0, that's an indeterminate form. So we have to use tricks. Rationals, those are fractions. That means we're going to multiply by LCD and simplify. Square roots, we're going to multiply by the conjugate. What are the other big ones that we see? Polynomials, we have to expand out the polynomials and then cancel and factor afterwards. Those are some of the big ones that we're doing. Trig is going to use trig identities. There's a lot of different ways to simplify. But yeah, for rationals, we multiply by the conjugate. Remember, the conjugate is almost the same thing, but the minus turns to plus between those two terms. Whatever you do to the top, you also have to do to the bottom. Then we FOIL it out in the top, and in the bottom we leave factored. And again, this is the formula called difference of squares. Look into difference of squares if you have questions about this shortcut. And it's just going to cancel to become the first thing squared minus the second thing squared. When you square a square root, it goes away. The bottom will leave factored. Again, algebra is really the big thing for all of calculus. Plus x minus x cancels out. We get the limit as h goes to 0 of just h divided by h times this square root. And now again, it's factored. You can cancel fractions as long as they have a common factor. And we get something really nice. Well, kind of nice. Because now we can use direct substitution, right? We can plug in h equals 0, and as long as x is not also equal to 0, we've got a really nice thing. This is going to be 1 divided by the square root of x plus 0 plus the square root of x. Well, that's the square root of x plus the square root of x. Well, I have one square root of x. I'm adding another square root of x. How many square roots of x do I have? I have 2 square roots of x. This is the derivative function. Derivative is the slope. So if I ever want to know the slope of the square root function, all I have to do is plug in the x coordinate into this slope function. The derivative function is a slope function. It tells me the slope, this red thing tells me the slope of this red thing. And that's going to be a big focus of the next video. Really quick, I can kind of show what I'm talking about, right? Like, if I'm curious, what is the slope of this square root function at 1? How steep is this? How steep is the function right here? We could use the slope function. Should be something positive, right? As we're going left to right. We're going uphill. So it should be positive. The slope should be positive. And it looks, I don't know, not that steep. Probably something less than 1. And indeed, if we plugged in x equals 1 into the slope function, we plug in 1 here, we get 1/2. The slope at the point 1, 1 should be 1/2. And in fact, if you write the equation of the tangent line at the point 1, 1 with slope 1/2, you do indeed see that that is the tangent line at that point in the square root function. The slope of the tangent line is a slope of the original function, which is the derivative. All right. And in fact, you can actually get really, really clever with a lot of cool stuff. I think that this would actually work with the slider function. If we just say the x value is just any value k, then the slope is going to be 1/2 times the square root of that. And the y value is always just going to be the square root of k. So if we just plug in different values into our slope function, ooh, look at that. If we plug in different values of our slope, different values into our, right, this is the derivative for the equation of a tangent line. This is the x coordinate. The y coordinate is just the square root of the x coordinate. That's the relationship between y and x. And then you can see the equation of the tangent line for different inputs. All the tangent line. So what's the edge of this domain? The edge of the domain is square root of x. 0, 0. X equals 0. That's the edge of the domain. What happens when we plug in? What if we look at the tangent line at 0? Well, Desmos won't show it to us. It gives us the tangent line when x is 0.1. But when we make that 0, there's no tangent line. Why? Because this derivative is not defined at 0. When we plug 0 here, we get undefined. All right. And in fact, if you look at our slope function, what's the domain of our slope function? Only positive numbers. X equals 0 is not part of the domain of this slope function. So this function is not differentiable at x equals 0. Something is differentiable at a point if the derivative exists. We would say f is differentiable on the interval from 0 to infinity, though, but not including 0. So that's tying some concepts together and really going on into future stuff. We'll do some more examples of this as well. But I want to get a couple more definitions before finishing this video. Okay. So f prime of x is the derivative function. It's the derivative at x. This is the notation that Newton used. Isaac Newton, and I think his first name is Gottfried Leibniz. I don't remember Leibniz's first name, actually. I hope I didn't mess this up on the video, but you can Google Leibniz. He used a different notation. He also developed calculus around the same time. And so you'll also see Leibniz notation a lot. All right, dy dx. So again, how do I want to write it? You'll also see y prime. You'll also see the derivative of y. These all mean the same thing. It's just a little notation. This is what's known as like the derivative operator. So we're like taking the derivative of y. Bunch of different ways that you can kind of see this. So like, and those aren't super important now, just you might see them. So if you see them and say, what does this mean again? Make a note to yourself to like look back here. Okay. And then there's one more thing, and this last thing kind of looks the weirdest for notation. The derivative at a point looks a little weird in Leibniz notation. That's the derivative function. And then we say evaluated at x equals a. This part right here, this bar, means evaluated at x equals a. And that's going to come into play. It's going to come into play some more in Calc 2 as well. So those are kind of the big things for notation. Just keep it in the back of your head that these exist. You don't have to memorize them, but as they appear, think, oh yeah, Jason mentioned these, and you can go back and remember what they are. All right, so that's pretty much it. We'll be doing more derivatives in the next video, and we'll also be showing graphical connections between two things. And that's where things get really fun, but also a little harder for some people because it's a different mindset. So stay tuned. Good luck on the problems, and let me know if you have questions.